And okay, so let's conclude the topic we are going to discuss related to cellular solid. We were just started to talk about a possible application of this kind of material as energy absorbers. That means for protection, for example, from impact, and with the ability to transform absorbed energy, in this case kinetic energy, which is absorbed by the impacting mass, for example, to heat. If we want to talk generally about the possibility to use a material as an energy absorber, we need to keep in mind three basic conditions which must be met. First of all, the structure, that is the material, must show a sort of homogeneous protection towards the impact direction, because we are not always in the condition to predict a defined impact direction. So this means that the behavior towards this kind of phenomena of the materials must be as homogeneous as possible. And this means that the microstructure of the materials itself must not show, let me say, discontinuities, but must be the same in all directions. This is the first condition to be met. The second one, since we are talking about something which must protect another object or a body, for example, this is an add-on. And so the materials with which the protection is going to be realized must be as light as possible. Then there is a third condition to be met. Since we are in presence of an impact, for example, this means that we have stress on the materials, which is going to absorb the impact and the energy related to the impact. And this means that the back materials is going to be subjected to a transfer stress. And so the third important condition is that we want to define a materials which is able to make the transfer stress to the body, which must be protected, to the component, which must be protected, as low as possible. And these are the three basic conditions to select a system and as a material which is suitable to be used as energy absorber. Well, according to our previous discussion, if we are talking about cellular solids or about foams, we match the third conditions, because these are, as we said, systems essentially void with a very low value of mass density, so they are light. Secondly, if we are able, and we are, to reproduce in the three-dimensional space the shape and size of the cells, this means that we can expect also to match the homogeneous condition. That is, we can expect that the behavior which is offered by the cellular solid is the same in all the directions. So we match the second condition. Now we have to discuss about the first one. That is, let the stress transfer to the component to be protected as low as possible for a defined value of energy to be absorbed. Well, to answer to this question and to see if this condition is met, let's have a look to the general, let me say, stress-strain diagram for a foam that we have already seen in compression. Even though, like in this case, the compressive stress is normalized to the Young modulus of the corresponding bulk solid. Well, we have already seen the lower curve, lower diagram. And if you want to compare this behavior with a behavior which can be expected in the case of a fully dense elastic solid, for example, we can clearly see, remembering that energy absorbed is the area under the curve, under the diagram. We can easily see that if we are going to work, for example, with a defined level of stress, like this one, for example, the area which is under the curve of the fully dense elastic solid is very, very low if compared to the area which can be under the curve of a foam. And this means that keeping low the stress, the amount of energy which can be absorbed by the foam, by the cellular solids, is relevantly higher with respect to the dense elastic solid. And so we can match with this kind of materials also the third conditions, that is, make the stress transferred as low as possible. And thus all these three conditions, which are essential in order to identify materials which is suitable for energy absorbers, are matched by cellular solids. And this is a quite important and relevant field of application of this kind of materials. This is another example showing to you, as if you want to compare that's one case of an elastic foam. If you want to compare the energy absorbed per unit volume, remember that when we are talking about a stress strain diagram, area are energy, but they are energy per unit volume, okay? In the case of a fully dense elastic solid, and cellular materials having different values, like reported here, of density, you see the top value is 0.3 according to our definition. Well, if we are going to work by fixing the normalized peak stress, that is the maximum stress transferred, you see here, this is the, for example, the energy which can be absorbed by a fully dense corresponding, obviously, elastic solid. And then this energy is going to be increased when we are going to move towards a higher value of mass density. But it's also very interesting, and most interesting, I would say, having defined that the behavior of the cellular solid is much more better than the fully elastic dense solid, to have a look to the blue here line, for which we can see that we are able to define or to transfer stress to the background to be protected, which are also two order of magnitude less than those we have in fully dense elastic solid, by absorbing, for example, also higher value of energy. Thus, in this case, confirming what we have just said 1 minute ago. Obviously, what is going to happen if we look to the stress strain diagrams of the cellular solid is that these stress strain diagrams for the same materials can have or can be parameterized, can have as parameter the mass density of the cellular solids. And what is going to happen is that if we are going to increase the mass density, or if we are going to decrease, obviously it depends on the point of view, the mass density of the cellular solids, we are going also to increase or to decrease the peak stress, the maximum peak stress, which is those referred, for example, to the plateau, for which the stress is more or less, as we said last time, constant. Thus, the mass density is one of the designing parameters in order to define properly, depending on the properties of the background, the maximum allowable stress when we use cellular materials for such kind of application. Can we or are we able to calculate the energy by volume which is absorbed? Yes, the answer is yes, because that's just an integral of the diagram. So this is the case, for example, for which we can define a constant value in the plateau of the stress. Then we have other contributions that can be added if we want to consider, in the case of open cell, also the work which is done by viscosity for fluid extraction when we have a compression applied on the materials itself. And this is something which is very well known to you because it's related to fluid behavior, as well as if we want to define also the case of closed cell, like on these slides, we need to take into consideration not the fluid extraction, like in the case of the open cell, but the fluid compression inside the cells, having materials not only on the edges, but also on the faces. And also this is a work made by pressure. Variation of pressure with refer to variation of volume, that is variation of deformation. And also in this case, we are able, very simply, if you know the geometry, obviously, and the geometry, I remember to you, is linked to this ratio, the ratio between the cellular solid density and the corresponding bulk material density to make an analytical evaluation of the energy, remember, per unit volume, which can be absorbed, generally speaking, having a plateau, by considering if we want the work done by viscosity for fluid extraction or the work which is done for fluid compression in the case of closed cells. So we know and we have all the analytic equations which let us make our calculation. What is the procedure which is generally used in order to properly select having defined a basic materials, for example, the mass density of the cellular solids which can match our designing condition? Well, we have just said that the stress-strain diagrams, they are related to the mass density. As you see, when we increase the mass density in this way, we are going to increase the peak stress. Another thing that we want to and we must consider is that the shape of this stress-strain diagram is not independent by the strain rate, which characterized, like in this case, we are discussing the impact behavior of the cellular solids. So first of all, what is done, and this is able also to to give to us as a result a graphic procedures, but if we want to make it analytically, we have the equation we have described before. We we establish, or we analyze, depending if we have to do lab testing or we have already the data, stress-strain diagram in compression, again, for a fixed value of the strain rate. And then if we have a fixed value of the strain rate, we have diagrams having as a parameter the mass density. So we can identify for each value of the mass density, the peak stress, that one which is corresponding to the plateau in the case of an elastic foam, or that one which is going to, due to buckling, I remember, that one which can be corresponding to the yielding of the behavior of the cellular foam itself, but also this we have the analytical relationship which we were discussing last time, but in any case graphically it's quite clear. And so we can, for each value of density, make our calculation of the energy which can be absorbed and the corresponding peak stress. So after having made this at a fixed value of the strain rate, we can define another diagram in which we report, and for simplicity purpose, it is again normalized by the Young modulus of the corresponding bulk materials, the absorbed energy per unit volume, that is the area, this area, okay, in terms of corresponding peak stress, okay, for a given value of the mass density of the cellular forms. And then we do have a maximum for each of these conditions for a given value of the strain rate, and we can draw the envelope which is going to, for each condition, that is the maximum, which is going to put together all the maximum values, okay, of corresponding, let me say, to the couple, between the normalized energy per unit volume and the corresponding peak stress. And this is made for just for one value of the strain rate. Then, and we can move through to the third step, this one, because we have just described the first and second, we can add all the other envelope for all the other values of strain rate. I mean, we have to repeat this procedure for another value of the strain rate, and so we can have this envelope, this is the first one, then the other envelope, this is the second one, and so on. Each one is related to a fixed value, as you see here, of the strain rate. And then we have finished, because we have all the three parameters on these diagrams, which let us to define which is the mass density of the solid, depending on the normalized peak stress that we want, and depending on the energy per unit volume that we want to absorb. Again, I repeat, for normalized to the bulk Young modulus, that is to the Young modulus of the bulk corresponding materials. And this is a graphical procedure. Some of these graphs are reported for the most common cellular materials on specialized tests. So in some cases, we can use directly these diagrams in order to make our selection. That is, define the value of, again, I repeat, of the mass density of the cellular solids when we know that we have to absorb a certain quantity of energy for a defined value of strain rate with a maximum peak stress defined by design, which is the maximum stress which can be considered allowable by the component, by the structure which must be protected. Here you have, for example, some examples. This is related to some elastic foams, polyurethane or polyethylene, like in this case. And you see here, this is defined for this value of strain rate for a defined value also of temperature, because in many cases, as we know, especially for polymeric materials, temperature is able to activate different behavior. And these are the experimental data. This is the first envelope that we define, and this is the case of an elastic foam. This is a case of a plastic form, that is a foam, a cellular materials for which we have to consider as peak stress the maximum stress for the yielding of the materials itself. And thus we have this final diagrams like those I showed to you. This is for polyurethane foams, elastomeric foams, and you see here, depending on the relative density and depending on the value of the strain rate, we have all the relationship between the energy which can be absorbed per unit volume corresponding and the corresponding peak stress. And this is the case of the plastic foam related to the polymethylato, which is the same materials to which this diagram is referred. Obviously, diagrams of this type have been done with different values, not only 10 to -3, of strain rate with velocity, which is going to characterize the impact on the materials itself. Let's have a look very shortly if it works. What is going to happen here is not going to work. Of a demonstration. Why? Let me see. Oops, because I have a pen, perhaps it for this. Yeah, a demonstration on how also experimental and visually, I would say, these kind of materials are effective. Okay, let's have a look. That's the case of an aluminum foam compared with a solid aluminum, where we have a 2 kilogram mass impacting. You see, this is the behavior compared of the bulk and on the left side and on the foam on the right side. In this case, we do have defined also the velocity, we have defined the mass of the impacting materials, that is the energy, and you see that nearly all the energy is absorbed by the foam in the right case. Otherwise, meanwhile, the solid aluminum block causes the mass, the impacting mass, to bounce. In this case, for a defined distance, but you see that the impacting mass does not lose most of its kinetic energy. This means that the solid aluminum is not going to absorb a relevant part of the energy. You see here, it stops. So energy is absorbed. And this kind of foam, in this case specifically, just to give to you an example, I repeat, is aluminum, is very, very effective and is generally speaking more effective than the corresponding solid materials. So these are also experimental tests which are made in order to understand the behavior of different types of foams with different types of cells and with different types of basic materials. Just to conclude today, let us remember another thing. This is just for you to remember something that you already should know. One of the main application of the cellular solid are in the so-called sandwich structures. The sandwich structures are very often, apart from, let me say, natural structure like those they are reported here in our body, but they are the sandwich structure made by an upper skin and a lower skin, which in most of cases for our applications, they are laminated composite materials. Usually they are polymeric based in terms of polymeric matrix composites reinforced with ceramic type, for example, with glass, with polymeric type fibers, for example, with aramid fibers like Kevlar. And then these two skins, the upper skins and the lower skin, are divided, are separated by a core. And this core is just a cellular material. It can be a polymeric foam, It can be a metallic cellular material, for example, Nomex, and whatever you want. These kind of structures, please remember, they are essentially, let me say, designed to work in bending. Why? Because if you remember, generally speaking, what it happens when we make a bending test on a beam, for example, we do have the maximum stress values on the upper and on the lower skin. So here in the upper and in the lower skin, we put composite-based materials in order to assure the presence of a suitable resistance of the system itself. It is a little bit less important, apart from the basis, obviously, the resistance inside, because the stresses are low, and thus we can think and we use a cellular materials to fabricate the core, provided that it has the resistance to stand with the lower stresses which are bending inside the sandwich structure. Obviously, the core must be glued with the upper and the lower skin, and if we are talking about sandwich materials in which the upper skin and the lower skin are made by polymeric-based materials, that's quite simple, because we can use the same resins, typically an epoxy-based resins, which is a structural adhesive for the system itself. And there is also another important concept that you should remember, that for a defined applied load on this system, the maximum value of the stress depends on the upper skin and on the lower skin, depends on the inertia momentum of the materials itself, and that depends on the distance between the upper skin and the lower skin. So we can make the suitable distance by using light materials, that is the core, that is using the cellular materials, which allow to us to have a composite structure, because this is finally a composite structure which is light and which is able to withstand with the maximum values of stresses which are localized on the upper skin and on the lower skin, being that made by composites, high-performing, high-resistance composite materials. And in the case of the sandwich structure, just to remember to you, I repeat, this is just a recall, usually or very often, not usually, let me say very often, we need to design the system in order to match a minimum value of the weight of the beam. And here you have the basic equations that I used in order to define the equivalent shear stiffness, the equivalent flexural, that is bending stiffness, the deformation at the center of the beam, if we are going to apply, for example, a centered load named as P, and thus, if we want to minimize the weight of this system by having defined which is the maximum allowable deformation for a given load, which is P, to minimize the weight, we must write the weight, and the weight is given by the sum of the weight of the upper skin and the lower skin. They are it is a symmetric system, so this is the reason because we have two. And then we must add to this also the weight of the core. And so if we have defined, for example, the length of the beam as of the sandwich as a design parameters, and we want to understand, I mean, we want to design which is the value of the core thickness called C and the upper and lower skin thickness defined as T, we can use these equations, these basic equations, for a fixed value, obviously, of the deformation at the center. And so we can write this final, which is the condition given as a design criteria. From this final, which is the relation between the deformation delta and the applied load P, we can come out with the value as in formula of the T, for example. This can be put in the equation, which is W, which is the weight, and then we can minimize, since we have an equations only depending by C, the other one are parameters defined during the design phase, we can define the value of C, that is the value of the core thickness. And after we have defined the value of C, we can come back and calculate the value of Phi, that is the thickness of the upper skin and of the lower skin. This is one example of applications. It's not impact, is a quasi-static system, which is the sandwich used in bending, in the presence of bending loads, but it's very common not only in aerospace structure, also in other, let me say, industrial applications. This is just the procedures we have defined before, let me say, with a sort of flow diagram. So there is nothing more added to the conceptual way of to proceed with respect to what we have said, just to put in a flow diagram. And we have also in this case the possibility, because in the specialized test it does exist, to define a sort of graphical optimization, graphical procedure. But I would say to you that these simple equations can allow to us also to make a very simple calculation in the case we want to define the general method to optimize our sandwich structure in order to match a minimum weight. I repeat, having defined obviously some design parameters, like for example the width B of the beam, the length, the total length L of the beam, the type of materials that we want to use as core, the type of several materials we want to use as core, that is the mass density of these materials, and then how much is the maximum deformation we can tolerate, and this is another design parameters in the center, when we are going to apply, for example, a concentrated load, which is the force P. Obviously, this can be repeated also in the case we do not have a concentrated load. We will have other formula, which are the basic formula of these composite structures. In the case we have a distributed load on the beam, or we have a combination of these two, let me say, extreme cases. Just remember, and I want to recall to you that when we are talking about sandwich structure, we need to make also some specific check in terms of the possibility to have different failure modes, because this kind of structure, which are composite structure, they can have, generally speaking, obviously that depends on the base materials. I just mentioned to you the most common cases, which is the case for that the upper skin and the lower skin is made by polymeric matrix composites, but we do have, or we can have also applications in which the upper skin and the lower skin, they are metallic alloys, for example, aluminum alloys, to stay in our field of aerospace materials and structure. What is going to change? It is going to change that if we are thinking to the possibility to have metallic alloys as upper skin and lower skin, obviously we are dealing with an upper skin and a lower skin which is at the time materials. which can show yielding. And so one possibility, if we are going to apply the load in this way, remember that we have compression on the upper skin and tensile stresses on the lower skin. It's to the possibility to have, for example, yielding of the material. So phase yielding is one of the possible failure modes of the materials itself, in case we are going to use ductile materials for the skins. And the failure load is defined as is reported. This is just for you as a summary of something you should have seen in the past years, not with me, with other colleagues, with other professors. This is the failure load, which must be taken into consideration according to geometrical parameter and according to, you see here, the tensile yielding strength of the materials itself. But we can have also other possibility. We can have buckling, for example, what is called phase wrinkling, which is obviously locally happening when it is present, buckling on the skins in which we have compression, that is on the upper skin. And also for phase wrinkling related to buckling, we can have evaluation, mathematical evaluation, which comes out from the equation of the continuous mechanics as to define the maximum value of the applied load, which can give rise to this failure mode. We can have core failure due to shear, and also in this case we have the possibility to define the maximum, the critical load for this situation which happens inside the cellular solids, that is in the core. Or finally we can have delamination, for example, delamination, which is the bonding failure among or between the skins and the core. And also in this case, that's related to shear stresses, which can be localized at the interface between the skins and the core. We can define a very simple equation based on continuous mechanics, which define the critical loads. So what does it mean, this table? It means that we have all the, in terms of design, apart from the situation we just showed to define as we can proceed to match the minimum weight, we have all the basic equations which allow to us to define which is the critical failure mode, because having defined, for example, a configuration, a material, we can use as the critical mechanism, obviously, the mechanism which is going to correspond to the minimum values of the applied load P in order to activate one of these failure modes. I repeat, yielding cannot be present always if we are going to use materials for the skins which have, for example, in the case of resin of epoxy matrix composites, which have essentially a linear elastic behavior till rupture, if we are going to use fiber length which are higher than the critical fiber length. Remember also this concept, which is a concept we discussed some years ago. I just remember to you the critical fiber length is that length of the reinforcement under which the failure mode of the composite materials is governed not by breaking the fibers, that is by breaking the reinforcement, but by pull out phenomena of the fiber itself. So if we are going to use materials and structural composite materials, the polymeric based, all match the situation for which the fiber length is higher than the critical fiber length. In this case, we can expect essentially a linear elastic behavior to rupture. So it makes no meaning discuss about possible yielding of the phases, which is a mechanism which can be activated for the case we have skins showing a ductile behavior. So we have a simple table. With this simple table, depending on the materials we have chosen, we just can define which is the critical failure mode of this kind of sandwich, of this kind of structure, sorry, the sandwich structure, which is an area in which, apart from the energy absorbing applications, the cellular solids are used. One sandwich, just to close the discussion of today, okay, we can have also some failure map, depending, you see here, aluminum phase. This is a case in which yielding we must consider, and so for each kind of sandwich configuration, we can draw up by experimental data, obviously, also by using theoretical, if we want, a failure map in which the mechanism of failure is evidenced as the critical mechanism of failure. I was just saying to you that one example, just moving to sport, of using sandwich structure is in ski. Not professional one, because professional skis for race, they are laminated, but for, let me say, less sportive people, not athletes, most of times they are made by an upper skin, a lower skin, and are formed materials, which is usually a polymeric base that is polyurethane foam. So in this case, the equation that we have defined before, they are used. Instead, just to close, if you are going about professional skis for racing, they are made of laminated wood. They are made one by one. And what is going to happen is that, in this case, is that we need to characterize each of the fabricated skis, because due to the manual operation during fabrication, but we are talking about racing apparatus, racing skis, they do, it's quite difficult to have a complete reproducibility of the behavior of the assembled ski. So we need to make a characterization, for example, in bending behavior of the materials itself. And then after the characterization, what is done in production is to define the couple of skis which can go together. That is the one for which the difference in behavior is the less evident, just to give to the athletes the possibility to use two skis having the same performance. But this just for your curiosity, in terms of, let me say, skis for racing, well, racing, yeah, but when we are going to talk about more conventional, more commercial skis, we do have another application of the sandwich structure, and thus another commercial, very diffused application of cellular materials, which are materials put inside the skis, and which is most of the time, as I told you, a foam, a polyurethane foam, that is a polymeric foam, since these apparatus, and if you think a little bit, you can agree with me, are essentially designed in order to resist to bending stresses, which are the main stresses for which sandwich structures are fabricated and are to which sandwich structure are dedicated. With this, we have closed and we have finished the lesson of today. And next time, that is on next Monday, we will start to talk about another, I would say, non-conventional class of materials, which are materials used for the fabrication of radar absorbing system, for example. Now, if you have some questions, please ask me. Ok, so if there is no question, I have a good...
Sì, scusi.
Eccoci, pronti.
No, giusto dal punto di vista geometrico, che cosa ci può essere utile magari tracciare un inviluppo di quelle curve, ad esempio?
Okay, your colleague was asking to which purpose it can be useful to have the envelope of the curves that we showed when we were talking about the graphical, let me say, procedure to select the cellular materials for an energy absorber. The answer is that you can have different combination, so that depends. I mean, you can define, for example, which is the peak stress for which you want, if you move on an horizontal line, for example, if you fix the maximum energy you want to absorb, since you have curves, diagrams with different parameters, you can have different combination of materials which can match the design condition in terms of peak stress or in terms of density, and depending on the strain rate, because usually when you have an impact, it's quite difficult that you can define a very reproducible value or fixed value of the strain rate, but you have to move into a range of strain rates so you can optimize the answer of your materials by selecting the proper value of the mass density and by selecting the proper value of the maximum peak stress. Did I answer to you?
Sì, penso di sì. La ringrazio, buon pranzo.
Grazie a lei. Any other question? Okay, so have a good weekend.